My name is Valentin Shiravi, and I want to talk to you today about GPU programming in Julia. I think it's helpful to start with a little bit of a diversion about computer architecture and talk about how we end up going from SIMD vector-style programming to SIMT GPU-style programming. One of the questions I like to ask people is, what is your mental programming model? And why the reason why this is important is because if you write down a program, I can either think about the fact that it is a series of statements that is going to be executed serially, or I try to think about how can I use the parallelism of the hardware effectively so that I can map my program onto the hardware. And so hardware offers many different forms of parallelism. And so the question becomes, how do we program so that we can use these different capabilities effectively? The lowest level of parallelism in hardware is instruction level parallelism. It is the fact that modern hardware can indeed execute multiple instructions at once. So you might have multiple compute units, you might have multiple floating point units that can do operations in parallel. Slightly above that sits data level parallelism, and so that is SIMD vector style single instruction multiple data or GPU style execution, where I have a huge amount of data and I really just want to do the same operation or series of operations over my data, and I have parallelism over the data itself. And then lastly, there's thread level parallelism, where I manually control the execution of a program, and I have different fibers of execution that happen in parallel, and they might communicate. They might either communicate with messages or they might communicate through memory. Looking at how we get to GPUs, as I mentioned, I want to take a short detour through computer architecture, and so I'm going to try to build up an intuition using a very simplistic assembly-esque programming style. And so I have this Julia function, which is actually a Julia code, so you can just copy and paste that into your Julia REPL. Please do not write code like this in real life. You should not use goto and label to implement a for loop. We iterate from, we start, in order to make this code simpler, I decide to start at n and then decrement down and run until we reach, as long as we haven't reached 0 yet. So this implements a for loop from 1 to n, or more accurately, a for loop from n to 1. And so all of these instructions could be translated directly into RISC-V assembly. And this is just to highlight the fact that I'm trying to be very simple in what I write down, and I unpack all complex examples. If you're used to Julia programming, this seems unnecessarily verbose, and indeed is so. So as a programmer or as a compiler writer, I'm worried about what are the data dependencies in the loop. You can see that this load of A, then A is used later here. X doesn't have a loop dependency, it's indeed a function argument. So C has a data dependency on A. A has one on I, because we load from A of I. And then the store is also a data dependency on the outcome of this operation. Mostly independent from our loop is the control flow operations, where we check whether or not, where we decrement our index variable and we check whether or not we need to re-enter the loop or whether or not we are done. Another way of looking at this is to ask the question, how many cycles on an idealized fictitious CPU, how many cycles of execution is this going to take? And so let's assume that a load has a 1 cycle latency, so we need to wait a cycle in order to use the result. That the floating point operation that we are doing here in cycle 3 has a 2 cycle latency, and that integer arithmetic has a 0 cycle latency. Now, since we have a dependency, we have stall cycles. You can see here in cycle 6, since the operation I equals I minus 1 does not have a dependency on the preceding statement, we do not have a stall. And so we have these pipeline bubbles, and we would like to minimize them. And one way of minimizing them is to say, okay, we can reorder these operations. And so we can move now cycle 7 up into cycle 2, into this pipeline bubble. And we need to take care of the fact that we changed I. So let's use I plus 1, which we can handwave away and say that that is a free operation to do. That fills out one of my bubbles, shortens the program, and increases performance. Well, are there other ways of improving the performance of this program? One option would be, before we get to that, let's look at, let's classify these cycles. Well, what are we spending our time? We're spending about 2 cycles on overhead, which I would classify as anything that is doing the index decrement and the checking whether or not we need to continue or jump to the loop. We have 2 stall cycles here, and these 3 cycles here are actually doing work. So what our goal should be to increase the amount of work in relationship to the amount of overhead we are doing, and to decrease the amount of stalls. So one strategy for that is unrolling. And so unrolling has the goal of reducing overhead relative to work. We will replicate the loop body by a factor. So if I say I unroll by a factor of 4, I will have introduced 4 copies of the loop body. And to do so, I will rename my variables, and I have to change the stride. So each loop iteration will now do 4 steps, and I also need to change my exit condition because of that. And I need to deal with the tail of the loop. So let's say we are iterating over 7 elements, and I'm unrolling by a factor of 4. Then I have 3 elements at the end that are not doing anything yet. So it tends to be that I need to do a little bit more work in the compiler to do that. We'll ignore the tail loop and focus on the central loop, assuming that if you have an unroll factor of 4 and we operate over like 1,000 or 2,000 element vector, the tail loop is a very small amount of the work. So if we unroll our example code by a factor of 4, you can see that I renamed the variable A to A1, A2, and A3, and so forth. And as I mentioned before, these index operation here are free on most architectures. Do we still have stalls? Yes, indeed we do, right? That we haven't changed the order here. We still have the same problem. If we count them up, we get about 12 stall cycles, and we have 2 cycles of overhead, and we do 12 cycles of works. So we're doing a lot more work in relation to overhead, so unrolling did its job, but we still have stall cycles. In order to reduce stall cycles, what we can do is we can now reorder this code. So this is the loop annotated completely with stalls again. And if I ask you to sit down and rewrite this code, you might realize that there is no dependency between A equals A1, A of I, and A1 equals A of I minus 1. There is no data dependency here. We need to be a little bit careful here. If we had multiple arrays, we would need to check for aliasing and issues like that. But since we're operating over the same array, this is very straightforward. And similarly, the operation C equals A plus X, there's no data dependency between C1 equals A1 plus X. So the data dependencies are the same. They are within our loop, our original loop, and they're not across loops. This allows us to do a drastic reordering where I can group all of the load operations together, and I group all of the addition operations together and all of the stores. By doing so, I actually am capable of removing all stalls. And I still have 2 overhead cycles, and I have 12 work cycles, so this loop is a lot more efficient and faster to execute. Now keep in mind, the amount of cycles taken per instruction, etc., is not from a real CPU. This is not, don't do this manually. Your compiler will do this in the background for you. What I also want you to notice is how regular this operation has become. Right, we load data regularly from A. We then do the same operation over A, and then we store the same. And so, wouldn't it be nice if I could tell my computer that I wanted to load 4 elements from A, or 8 elements from A, or 16 elements from A, and then over those 16 elements I want to do an addition operation, and then I want to store all 16 elements at once. And that is what single instruction multiple data vector style parallelism is about. Instead of reasoning about individual elements, I reason about vectors, chunks of data at once. So, as a programmer, I normally have the model that my code will be executed in linear order. But in reality, to instruct the parallelism between these operations, they use instruction level parallelism, so they can execute more than one instruction at a time. They have deep cache hierarchies. So if you ever look at like an Intel processor and you look at the cache hierarchies, you have a level 1 data cache, a level 2 cache, a level 3 cache, and so forth. And the way those caches are manipulated is one of the reasons why modern CPUs are fast. Like, moving data is very slow, so if I can predict which data you need to do the operations, I can preemptively load data into my cache hierarchy. You can exploit instruction level by being a superscalar architecture, by issuing multiple instructions at once. You can do out-of-order execution or speculation. So if you've been attentive to the news, you might have heard about like issues with modern CPUs around speculative execution. Well, part of speculation is to say, I guess what the result of my loop condition will be, and I will guess that you will continue executing the loop, so I will start executing the next iteration of the loop, despite me not knowing yet whether or not I'm allowed to. And so if I guessed wrong, I have to undo all of the work I did. Because for the programmer, the execution has to seem like it was linear, even so we are executing it non-linearly. Out-of-order execution is to say, oh, this execution is doing something, and this other one is not has no data dependency, so I can pull it out earlier. That's what we've done with the reordering. Into speculation comes prediction, as I mentioned. So sometimes I need to guess, predict values. Branch prediction is one of them. Cache line prediction, etc. So if I'm focusing more on a data parallelism world, I would say, okay, I don't rely as much on the processor, and I don't rely as much on the compiler. I know pretty much exactly the sequence of instruction I would like to do, and so I would like to communicate that to my processor, and I want to use its vector capabilities, and so I can write explicitly parallel code. So that is explicit vector programming, Or alternatively, if I know that I'm targeting, that I have a GPU available, GPUs are inherently parallel devices, so it might make sense to actually write an inherently parallel code and not expect auto-vectorization or a compiler to be able to prove that my code is parallel. So typical data parallel programs are in Julia. If you do a map or a podcast, those are like I'm doing the same operation over all elements of an array. Like bigger problems is you're solving a PDE. While you have a lot of communication between different spatial discretizations, effectively you're solving the same systems of equations over a big grid. And so you can do that solving in parallel. So one way of doing this is to use a single instruction multiple data, which is an explicit vectorized programming model. And in Julia you can use SIMD.gl, which is one of the nicer ways that I have seen of actually doing explicit vector operations. And so we are back to our for loop. We take a stride of 4 because we have decided that we want to use vector operations of the size 4. And I know that because I looked up what my CPU likes. And so I know that with the data type float64, vector length of 4 is AVX 256, and therefore probably a good choice here. And if you think back to our original program, keep in mind that stalls in theory, while we will have stalls here as well, but there are per instruction and not per element. And so we're now doing 4 times the amount of work, but for the same like sequence of operations. We reduced overhead because we're now saying, oh, this is basically like our unrolled loop, except that we do it in 3 instructions. And 3 instructions here process 4 elements, so we have 2 overhead instructions and we amortize the overhead across our 4 elements. The vload here loads a consecutive block of memory, and the vstore stores a consecutive block of memory. So starting at index I, it will store the vector C to A. And we could take this a step further and say, oh, I know that a vector load has a latency of something. Now let's unroll the code by another factor of 4. Then reorder the code so that I'm doing 4 vector loads in parallel. And indeed, if you look at the compiler output of Clang or LLVM, you will often see this patterns of vector instructions with 4 unrolled 4 times. But generally speaking, since I'm doing more work, latencies will be higher. So again, don't worry about the latencies per se, but think about the parallelism that you want to express. When I'm looking at a SIMD code like before, I mentioned that the vload A is loading consecutive memory. So can I load non-consecutive memory? And so indeed, yes, we have a gather and a scatter instruction, and that allows us to work with sparse data through indirect indexing. So we create an index vector, which is the same length as our SIMD length. We use the gather instruction to load the data, and the scatter to write the data, but keep in mind that these instructions are less efficient than a vload and a vstore. So here's an example of this. We take an index vector 1, 2, 1, 3, 2, 4, and we gather the data, causing us to obtain a vector where the elements 3 and 2 are flipped around, and we can scatter the data back into the same locations. So this is a swizzle. One other thing that you might notice is, well, so far I've only talked about straight line loop bodies. What if I need to do a branch? Whether or not I want to check that A is a certain element is equals to 0, and I want to do something different, right? So as an example, say we iterate over a random vector of integers, and I want to check that A is, if the element is even, then I want to negate it. How do I take this code that now has a control flow dependency on the value of A, and turn that into vectorizable code? In SIMD.gl, what I can use is masking. And so as an example, I load a vector from A. I then calculate my index condition, my control flow condition as a mask. I then do all of the, and then invert all of the elements of A. And then I select with the vector if else, based on my mask, the elements from B and A. So what this means is that instead of only executing the if statement in case that A is equals, I will always execute the body of the if statement, but then I will merge the results of that if statement back with my output, depending on the mask, whether or not I should have taken it. So I'm doing more work. I'm doing the inversion always, but I can benefit from vectorization. So in many cases, like if I were to use an auto-vectorizer, using an if-else here would actually allow me to then would allow the auto-vectorizer to vectorize my code here. There are hardware solutions for this. So as an example, if you look at some interesting accelerators like the NEC Aurora VX, you can use predication, where each vector operation takes a predicate. You have mask load and stores on the Intel CPUs. There are also compiler solutions like the Intel SIMD compiler, which will translate scalar code into vector code with mask loads and stores. And then OpenCL and CUDA also have the capability of executing what they call divergent branches, and we will talk about that in a little bit. GPUs really are just vector engines, but the way we program them is different. Instead of doing an explicit vectorization, we do an implicit vectorization. So as an example, this is a CUDA program written in Julia. It takes a kernel, this is often what we call GPU programs, and that kernel takes an array, and it implicitly asks the question, what is my lane? This is called, in CUDA parlance, that's the thread ID. And it then loads the data element that scalar program is responsible for. It then executes the scalar program with the A as we had before, and then it returns. This is the body of our for loop, and this index is implicitly derived. So we can then launch this kernel on the GPU with the add CUDA macro, and we can tell it that we want as many threads as A is long. And so the hardware will then automatically handle the parallelism for us. Keep in mind that the warp width, or the native vector width, is 32. So 30, where previously I used a vector width of 4, on the GPU it's always a vector width of 32. And so 32 lanes will always do exactly the same thing. And so if one of them diverges, all of them have to diverge. And so we go back to this issue of masking. So A modern GPU, as an example, the NVIDIA V100 has about 80 cores. NVIDIA calls them streaming multiprocessors, which is weird. And on each of these 80 cores, you have about 64 functional SIMD units. There's a whole bunch of white papers and a blog post about like going into depth into the architecture. I just wanted to briefly show you like the V100 chip from a top-down perspective. And we'll zoom in and we see these are the shared multiprocessors, the cores that we've been talking, that I mentioned just before. And we have a big L2 cache, and then we have communication from memory, we have communication with NVLink, we have PCI Express connections sitting on the edges, and then we have the processors separated into blocks. And then if we zoom in a little bit more, you have this single shared multiprocessor, and it has an amount of registers, it has an amount of L1 data cache, and you have these floating point 64 operational units, you have integer arithmetic units, you have floating point 32 units, and you have load and stores and special functions. And so each shared multiprocessor will execute warps together over these available hardware resources, and it will use a variant that I would. It is trying. So the goal of a GPU, in contrast to a CPU, is to hide latency by exposing massive parallelism to it. So a GPU does a lot less clever tricks, but it has a lot more parallelism available. And that makes a lot of sense when I'm looking at big data like neural networks, matrix multiplies. And I want to hide the time it takes to do a data load, as an example, by executing a lot of other operations that either will also start to trigger data loads or that will actually do arithmetically intense operations. So I get to hide all of the time it takes by having a simpler architecture with more parallelism by actually doing more work. And so it's throughput optimized instead of latency optimized. A modern CPU tries to give you the answer as quickly as possible, whereas a GPU tries to give you as much of the answer as possible. This is the end of our brief diversion into computer architecture, and the next video will be about how to actually use GPU programming in Julia.